This first slide is the whole motive for me making this video. Here we have the formulas to find the value at a position n, starting with the value in position 1 plus the common difference times n minus 1. Now down here we have the same formula where we're trying to find the value at position n, but here we're starting with an a sub 0 value, and therefore you have to subtract 0 from n. So let me explain what I mean by that. Let's say you're trying to find the value at position 3. Okay, that position 3 is considered the ending point. Here we're going to start at a sub 1. So if we start at a sub 1 right here, and we're trying to find the value at position 3, we're going to start with the value at position 1, which is 4, and then we're going to add the common difference times n minus 1. So the common difference here for this particular sequence is plus 2. So we're going to have 2 times n, with the ending point is 3, minus the starting point. 3 minus 1 is 2. Therefore, we're going to have a value at position 3 of 4 plus 4, or 8. And that checks out with what we have here. Now look, we can get the same answer on the bottom using this formula, but this time if we're trying to find a sub 3, and we're starting with the a sub 0 value, so the a sub 0 value here would be 2. It's going to be 2 plus the common difference times n, which is 3, minus 0. Now we're going to have 2 plus 6 equals 8. So you get the same answer. So it's very important that if you're going to start with the value at position 1, if you're going to start here, then you subtract 1 from your n that you're trying to get. If you're going to start with this value at a sub 0 here, then it's important that you subtract 0 from n when you do your computation. We are told that in exercises 15 through 18 that we're dealing with arithmetic sequences, and we're asked to find the common difference, a sub 10, a recursive rule for the nth term, and an explicit rule. So folks, recall that with an arithmetic sequence, we are adding or subtracting as we move along. Okay, and recall that when you're dealing with a sequence, there are two issues. There's a value and there's a position. Okay, the n is the position. If we were to graph this, that would be the x values. This would be the y values. The n would be the input. The a would be the output. So as we label these sequence positions via n, in this particular case, the value at position 1 would equal 6. The value at position 3 would equal 14. Okay, so the first thing they want is the common difference. And the common difference is how are we moving along from place to place. So you could see here that we're moving along by adding 4. So the common difference, abbreviated with a D, is plus 4. Now that could be a negative. You could have a sequence decreasing as it goes. And the way you get this, if the math isn't as easy as this, is you take that term first and subtract the term before it. So it's right minus left, and that will give you the common difference. It's like saying there are two brothers, one is 11 years old and one is 16. What's the age difference between them? Well, you take the right and you subtract the left. You take the older and you subtract the younger, and you would get 5 years. Okay, so that's part A. We have a D value of plus 4. Now they want the value at a sub 10. So let's go ahead, excuse me, and get the answer in a non-elegant way. And that is just continue to move along. Okay, now we can't do this for practical purposes all the time. hold on, let me just get our a value. So this will be plus 4, 22, 26, 30, 34, 38, 42. Okay, so we know ahead of time that the answer to this part of the problem, a sub 10, the value at position 10 is going to be 42. But this is not an elegant way of doing it. What if they wanted the value at position 127? So we have to have some sort of formula, some sort of computation to get the value at any given n value. Okay, the a value at any given n value, the value of the sequence at any position n. Okay, so let's talk about how we got to 42. Well, we started with the first amount. Okay, so here is going to be a sub 10. How did we get there? Okay, so we start with the first amount, which is 6, and then we're going to add to that. Now, what are we going to add to that? Well, each step we take, one step. Let me get rid of that plus 4, because that's distracting. Each step we take, we're going to add 4. Okay? So basically, we want the number of steps times 4. And we're going to add that to the first value, and we're going to get the value wherever we end up. So the question is, how many steps do we take? All right. How many steps are taken? So rather than count them out, let's do a shorter move. Let's go from position 1 to position 5. How many steps was that? 1, 2, 3, 4. So to go from a sub 1 to a sub n, we took n minus 1 steps. Okay, if we go to 5, it's 4 steps to get there. So the number of steps is going to be n minus 1. Okay, so in this case, we are doing, our n value is 10, so we're going to end up taking 9 steps. So we're going to have 6 plus 9 times 4, and that's 6 plus 36, and that is how we get to 42. Next, we are asked to find a recursive rule for the nth term. Now, folks, the recursive formula is an intimidating name for a simple concept. So in an arithmetic sequence, look what's happening. We're starting with 6 at position 1 at n equals 1. And in this particular sequence, we're adding 4. Okay, we're adding 4. So that means our common difference, our d value, is 4. Now look how simple this is. Okay, look what this formula is saying. It's saying go to position n and look at its value. Okay, so let's pick position 3 right here. All right, so if you want to know the value at position 3, that's what a sub 3 means. What do? Well, you go to the position that's to the left of it. Okay, so you go to the value at the position to the left. How do you go left in math? You subtract. How do you go left by 1 in math? You subtract 1. So we're going to go to the a sub 2 position. So here we have 10. All right, that's the value at position 10. And then we're going to add 4. I mean, how much simpler could it be? This term is intimidating, I get it. But the way to think of this is whenever you hear the word recursive, think of the neighbor to the left. Okay, so if they want a value here, okay, whatever position that is, let's call it n, you go to the left. Okay, so how do you go to the left? This is n minus 1. And then you get its value, whatever that is, a at n minus 1, and you add the common difference to get to where you want. It is just that simple. So in this particular example, we just about done it, but let's do it formally. The recursive formula is if you want a value at position n, you go to the neighbor next door and you add the common difference. So here, actually that's, oh, we just need to put the common difference for this particular problem, and that would be 4. So let's just rewrite it formally. A to the n equals n, a to the n minus 1 plus 4. So think about it like this. A reclusive neighbor, okay? As soon as you hear the word recursive, think about a reclusive neighbor that lives right next door to you on the left. Next, in part D, they are asking for an explicit rule for the nth term. So here is the explicit rule, and I think what they're looking for is a general rule to use for this data that's presented. So let's call this a sub n, and instead of a sub 1 here, we're going to put 6, because that is our a sub 1 value. And then instead of d, we're going to put 4, because recall, that is how we're advancing in this particular sequence. That's our common difference. And then let's leave this as n minus 1. So if we distribute the 4, we're going to have 4n plus, 4n plus 2 as our general formula. So let me write that again here. So the explicit formula for this particular sequence is this right here. Now, let's just test that out and see if it makes sense. So let's randomly, this is the sequence extended out, so let's randomly pick an n value. Let's investigate a sub 9 and see if our formula is correct. So for a sub 9, we would do 4 times 9, which is 36, plus 2 would give us 38. So yes, indeed, our explicit formula for this sequence is correct. Next, in this set of exercises, they're asking us to find the terms 1, 2, 3, 7 of the recursively defined sequence. So folks, when they say terms 1, 2, 3, and 7, that's the n value. That's the position of the sequence. Okay, so I went ahead and started it here. Now they gave us a sub 0 equals 8, and this is the recursively defined formula. So look at this now. The position, the value at position 0 is 8. Here's position 0, here's the value 8. Now folks, look at this recursive formula. Whenever you hear the word recursive, I want you to think of this image. I want you to think of that's position n, and here's the value at position n, and you have a reclusive next door neighbor. What position is he going to be if he's to your left? Well, he's n minus 1. If this is position 7, that's going to be position 6. So the value at n minus 1 is going to be the value that's to the left of you on the sequence. Now, to show this, let's now look at the formula. What are they saying here? They're saying the value at n, that's this black box, equals the value at a to the n minus 1, that's the red box, minus 4. So they're telling you that that's your d value. To get from red to black, you got to subtract 4, like so. Okay, let's fill out our sequence and see if this is true. So we start at a value of 8 at position 0. We are now going to subtract 4. So we're going to have 4, 0, minus 4, minus 8, minus 12, minus 16, and minus 20. Okay, so one of the things they wanted was the value of a sub 7, and we got that as negative 20. Okay, let's see if the recursive formula works. Let's pick a random value here. Let's pick a sub 5. Now, does a sub 5 equal a to the n minus 1? That would be a sub 4 minus 4. So here we have a sub 5 is negative 12. So does a sub 5, which is negative 12, equal, okay, we'll put a question mark, we don't know if it's true yet, a sub 4, which is negative 8 minus 4, and the answer is yes. Okay, so we now know that we interpreted it, the recursive formula, correctly. We now have our sequence with a d value of negative 4. Okay, folks, at this point, I want to go ahead and develop an explicit formula for this sequence. Okay, now recall, in the last problem we did, this was our sequence. Now look at this. The explicit formula was as so. A sub n equals a sub 1 plus d times n minus 1. We interpreted this as this is your starting amount, this is your common difference, and this is the number of steps we took. Okay, and how do you determine the number of steps that you take? If you start at position 1 and you end at position n, how many steps does it take to get here? The answer is n minus 1. Now, why does this formula make sense? Here's why. Because if you start with, if you're trying to find the value at position n, you have your starting amount, which is a sub 1, the amount at a sub 1, and then you're going to add. Okay. The d is the amount that you're adding per step. And then you're going to multiply that by the number of steps. So you could see how, I don't like this in the corner here. This is really important. Let's bring this out here. Okay. So you see here that the amount that you have further down the sequence is the amount where you're starting and the amount that you're adding. All right, let me erase this and change this on top to the d value that's right here is the amount added per step. Amount added per step times the number of steps. The steps cancel out. This is the amount added to the original amount. Now look at this. Look at our sequence here. What's the difference? Our sequence here now starts with a sub 0. So you cannot use the same formula. That's really the whole crux of my video here today. So let's erase some of this. Keep some of it. All right, I want to keep this. I appreciate your patience, everybody. Okay, so now let's look at our formula here. Our a sub n is going to start at a sub 0, and we're going to add the common difference of the number of steps we take. That is going to be n minus 0. Now, why is it n minus 0 here and n minus 1 here? Because in this particular example, we're starting at 0. So if you want to figure out, okay, here's your starting amount. Now, if you want to figure out the amount that you're adding from 0 to n, how many steps are you taking? The answer is n minus 0. Remember, if you're trying to figure out the age difference between a brother that's 18 and a brother that's 19, how many years do you have to get from 11 to 19? You do 19 minus 11, and the total is 8. So that's why you have to be careful. You can't immediately put n minus 1 here if you're starting with a sub 0. Okay, let's test this out because we have the answers. We have the answers, so let's see if this formula is correct. Okay, let's pick a random a sub n. So let's say a sub 4. Okay, we're going to take our a sub 0. The amount at position 0 is 8. Then we're going to add the common difference, which is negative 4 times n minus 0, which is just n. And in this particular example, our n value is 4. So this becomes minus 4 times 4, and that's going to be 8 minus 16, which is none other than negative 8. So that matches. So this is the correct formula for this sequence if and only if you're starting at a sub 0. Okay? Now, folks, you can start at a sub 1 if you want. You're not committed to starting at a sub 0 here. You could start anywhere on this sequence as long as you follow the rules that this here has to match that. This here has to match that. That's your starting point. Your starting point. N is your ending point. As long as you have n minus the starting point as the number of steps you take, you will be okay. Here it is. N minus the starting point. There's your starting point. Okay, let's play around with this. Let's play around with this and see if it works. Again, we have all the answers up top. Let's find the a sub n value if we're starting at a sub 2. Okay? And let's see if we're right. So this formula is saying we're going to start with the amount at a sub 2, the amount at position 2. And we're going to add to that the common difference times the number of steps we take. How do we know this is the number of steps we take? Because n is our ending point, and a is the ending point, and 2 is the starting point. Okay, so let's pick a value and see if we're correct. Let's see if we can predict accurately the amount at position 5. So that's going to be the amount at position 2 plus negative 4 times 5 minus 2. Okay, so the amount at position 2 is 0. So this is going to be a sub 5 should equal the amount at position 2 minus 20 plus 8. So the amount at position 5 should equal negative 12. And indeed it does. Let's try one more position to show you that this concept is correct. All right. Let's do the amount at position 3. No, that's not what I want to do. I want to find the position, the amount at position n, starting at position 5. Okay, so we could start with position 5. There's no rule against that. All right, maybe this is an easier number to work with. In this case, it's not. But I want to start at position 5 and produce an explicit formula. Here we go. It's going to be the amount at position 5 plus the d value. Here, let me write it out in general forms first. The amount at n is going to be our d value times n minus 5. Why? Because we're going to start with an amount at position 5. Then we're going to add more. How much more are we going to add? Well, we're going to have the amount is d per each step. Well, let me put step in the denominator. The amount d for every step times the number of steps. That's what we're going to be adding. So in this particular case, our starting point is 5. Our ending point is n. The number of steps is always the end minus the starting position. Okay, so let's pick a number and see if this works. Let's figure out what the amount is at a sub 8. Okay, that's not on our screen yet. Let's get it on there. So minus 4 would get negative 24. Let's see if this works. Okay, so the amount at a sub 5 here is negative 12 plus our common difference is negative 4. Our end value where we're going is 8. Our starting value is 5. So this is negative 4 times 3, otherwise known as negative 12. So does the amount at position 8, does a sub 8, sorry, that's an A. Does a sub 8 equal negative 12 minus 12, negative 12 minus 12, which is negative 24? Indeed, it does. Folks, I want to review this concept one more time. I apologize if I'm being repetitive, but the emphasis of this video is that this is not always in our formula, n minus 1. Okay, that value here depends on where you start. It's going to be n minus the starting point. Okay, so here we go. This is saying the amount at your ending point, whatever you want. Let's here in this example pick the amount at an ending point of 6. So we're right here. If you want the amount in position 6, that's an n value. Okay, but we want the amount in position 6. We take the amount in your starting point. Pick a starting point. Let's use 3. Okay, so we're going to take the amount in position 3, and then we're going to add to that. What are we going to add? We're going to have our d value, which in this problem is negative 4. And now we're going to multiply that by the number of steps. Now, when we talk about n minus the start here, we're talking about n values, not a values, not amounts, because we want the number of steps. So to figure out the number of steps to go from position 3 to position 6, we have to use the end position. That's right there. That's 6. That's an n value, not an a value. The end, n as in November, end as in end of the day, n as in November. The end n value minus the n start value. So that's going to be, in this particular case, 6 minus 3. And that's because there's 3 steps. 3 to 4 is 1, 4 to 5 is 2, 5 to 6 is 3. So that is going to be how many times we're adding negative 4. Okay, let's complete the math here. Our a sub 6 value, which is what we're looking for, is going to equal the amount at a sub 3. Not n equals 3, the amount at position 3. That's going to be negative 4. And to that, we're going to add negative 4 times 3. So this is going to be negative 4 minus 12, otherwise known as negative 16. So if we're correct, then the amount at position 6 should be negative 16, and indeed it is. This value here, that in parentheses, is not always n minus 1. It depends where you start. Look what we did here. Here we did n minus 3, right? Look at this. Let's rewrite this. Let's rewrite this in yellow. Here we did a of 6, that's our ending point, equals a of 3, that's our starting point, plus d times n minus 3. Look at that. Look how different that is. It's because we're starting at 3. And n minus 3, in this case 6, is going to give us the number of steps that we multiply by the common difference, and we add that to the amount of our starting point. Okay, folks, let's have a little fun and let's go backwards. Okay, suppose we want to find the amount at position 2, but we're going to start at position 5. Okay, so we're going to go backwards. And let's show how the intuition of this formula makes sense. Okay, so if this is our end position, we're trying to figure out the amount at position 2, and we're starting here. Let's see where the formula takes us. So we're looking for the amount at position 2. We're starting at position 5. That's the amount at position 5. And to that, we're going to add the common difference times the number of steps we're going to take. And the number of steps is always the end n position. End is in end of the day. N is in November minus the starting n position. Okay, so a sub 2 equals the amount at position 5, which is negative 12, plus the d value, which is negative 4, times the end position, the end as in end of the day, n as in November position is 2, minus the starting position, n value is 5. So that's going to equal negative 12 plus negative 4 times negative 3. That's going to be negative 12 plus 12, and it should be 0. And indeed, if we look at the answers, which are up here, the value at 2 is in fact 0. Again, folks, the emphasis is that this n minus can be anything. Look at this. Here, it's n minus 1. Why? Because the end, as in end of the day, n position is that, and the starting n position is that. Look here. The end n position is 2. That's what we want. The starting n position is 5. That's where we started. Next, let's move our discussion to geometric sequences. So here, in this set of exercises, we're asked to find a common ratio, the value at position 7, recursive rule, and explicit rule. Okay, so we're doing number 19 here, and we start out with 2, 6, 18, 54. And I went ahead and continued. I identified the common ratio as 3, which of course is just 6 divided by 2, 18 divided by 6. So that is our R value. Okay, now, folks, when it comes to finding the amount at position 7, I went ahead and found it so we know we have the answers. So as we build our formulas, we could check our answers. Now recall, in the arithmetic sequence, in the portion of the video we just finished, we have to be careful that this n value matches that n value. Okay, the n is in November. That's our ending point. We do the ending point minus the starting point. Okay, if you wanted to start at a sub 0, then it would be plus n minus 0 times d. Okay, it's the number of steps. The way you determine the number of steps is the last n position minus the first n position. Okay, now let's move to geometric sequences. Folks, it's the same idea. Okay, it's the same idea. We're down here now. We're down here now. Okay, it's the same concept. Look at this. If you want to find the nth term, if you want to find the amount at the nth term, that's the ending position. Right there, that's the ending position. You do the r to the n minus 1, and that's a 1 only because there's a 1 here, only because that's the amount in your starting position. You might see it like this: a sub n equals a sub 0 r to the n minus 0, or a sub 0 r to the n. So you've got to be very careful. If they list values, okay, if they have n values, and here's your a value, and they have position 0, 1, 2, 3. If they have position 0 there, okay, you can't willy-nilly put this first amount, okay, let's say this was 10, and use this formula like this. You can't have 10 to the r to the n minus 1. Because look, that is the amount in position 0, not position 1. You have to make sure that you have this amount in position 1 if you're subtracting the 1 in the exponent. And we're going to see that in detail in a moment. Okay, let's go ahead and find the amount at position 7. Now, we already know what it is, okay, but let's do it in a more elegant fashion. Okay, so the formula to find the amount at a position n in a geometric sequence is the amount at the first position times your r value raised to the n minus 1. This is the number of steps you take. This is the number of times we're going to multiply by r. Okay, so in our example, if we're trying to find a sub 7, we're going to start with the amount at position 1, which is 2. We're going to multiply that by our r value raised to 7 minus 1. Why is that? Because look, how many steps do you take to get from 1 to 7? 1, 2, 3, 4, 5, 6. How many times are we multiplying by 3? 1, 2, 3, 4, 5, 6. That's how many times we're going to multiply the initial amount by 3, which is our r value. So how do you get 6 steps without counting on your fingers? You do the end n position minus the initial, the start. We're starting at 1, we're ending at 7. 7 minus 1 is 6, and we're going to have 2 times 3 to the 6, and indeed that is 1458. Okay, folks, let's have some fun with this formula, with the intuition of the formula. Suppose I want to find the amount at position 5, and I want to start at position 3. Well, we would take our r value, and instead of using n minus 1, I don't want you to memorize this formula. I want you to recognize that that starting position, here n equals 3, we're going to do our ending position minus the starting position. Just like that 1 matches that 1, this 3 matches that 3. Okay, now in this case, we're trying to get to 5 for our n value. So let's fill in our values. A, or the amount at position 3 is 18. Our r value is 3. We're trying to get to number 5. So now we're going to have 18 times 3 to the second power, and that indeed is 162. So Again, the benefit of going ahead and getting our answers means we can play around with this formula and check our answers like so. Folks, the way to think of this formula is the amount at your end position, end as in end of the day, is the amount at your starting position times your common ratio raised to the end minus the start. Now look at this. Suppose we wanted to find this. Suppose we wanted to find the amount at position 3, but we're starting at position 7. Okay? We're going to go backwards, something you don't normally do in these problems. Let me show you that it still works. The intuition still works. Here, the amount at the end position, we want to know what that amount is, equals the amount at the start position times r raised to the end minus the start. Okay, here's the amount at position 7 is 1458. There's our common ratio. 3 minus 7 is negative 4. 1458 divided by 3 to the 4th is 18. And folks, that confirms with the amount of 18. This is really the way to think of the formula. The amount at the end n position is the amount at the starting end position, whatever it is, whether you're going 7 to 3, 2 to 7, 1 to 7, 0 to 7, it's always the end n value, end of the day, November value minus the starting n value, and that's in the exponent for your common ratio. Okay, now that we found the a sub 7, the amount at position 7, they ask us to find a recursive rule for the nth term. So again, folks, when you hear the word recursive, I want you to think of a reclusive neighbor. So if we want the recursive formula to get a value at a position n, what do? We go to the position to its left. What is that going to be? N minus 1. So we're going to take the amount at n minus 1 and multiply it by the common ratio. So the amount at position n is going to be the amount at position n minus 1 times the common difference, which in this case is 3. Okay, finally, in section D, they want us to find an explicit rule for the nth term. So I think they want us to find an explicit rule for this particular sequence. Okay, so here was the general explicit rule. So let's just go ahead and make this match what we have for a sub 1 and r. So our explicit rule is going to be our a sub 1 value, which is 2, times 3 to the n minus 1. So that's our a value at the 1 position. We have our 1 here, so they match. So wherever you want to go, you should be able to use this formula. So let's give it a try. Let's see if the a value at position 3 does equal 2 times 3 to the 3 minus 1, which equals 2 minus 3 squared. 2 times 9 equals 18. So indeed, this explicit formula should work for any n value that you're trying to get on this particular sequence. Let's test our understanding of the geometric formulas when presented with a little curveball here. So we're going to do number 11. So let's look at number 11. For these exercises, they want us to find the terms 1, 2, 3, and 7 of the recursively defined sequence. Okay, recursive, we think neighbor. So look what they're telling us here. Here they're using B instead of A for the amount. So this is saying that the amount when n equals 0, but they're using K. Okay, so they're trying to trip us up here. So normally we have an n value and an a value where n is the position. They are using K and B instead of n and a. Okay, so look what they're saying. They're saying B at position 0. That's the amount at position 0. Okay, so we're going to put 0 here. Let's just use n and a. Okay, so their n value at 0, the value is 2. Okay, they're giving us the starting point. Now, look at the recursive formula. Look what this is saying. They're saying B at any value of K. That's just like us saying the A value at any position value of n equals 3 times B to the K minus 1. The amount at K minus 1. That's the same thing as us saying the amount at n minus 1. So there's the neighbor. How do you get, okay, here we go. Let's draw a box. So if you're trying to get to the black box, A sub n, you go to the red box, the reclusive neighbor to the left, that's A at the n minus 1 position. And how do you get from red to black? You multiply by 3. So the recursive formula gives you your R value, just like it did give us the D value when we did arithmetic sequences. Okay, so now that we know our R value, we can progress all the way up to these terms. Okay, so let's write them in. So they want 1, 2, 3, 4, 5, 6, 7. We're going to be multiplying by 3. This is going to be 3 times 2 is 6. 6 times 3 is 18. 54. Okay, let's stop right there for a moment. And let's now find A sub 7 without multiplying by 3. Let's see if we can do it more elegantly. Okay, so here we're going to say to ourselves that the amount at position n is going to be the amount at position 1 times our R value, which is 3, to the n minus 1. Okay, let's see if that works. Let's test it out. Okay, let's say we want to find the position at n equals 2. Let's see if we're right. So the A value at position 2 is going to equal the A value at position 1, which is 6, times 3 to the 2 minus 1 equals 6 times 3 to the first equals 18. Okay, so I am confident that this is our correct formula. So let's do it now for the 7th, because that's what they want. So the amount at the 7th position, right here, should be the amount at the first position, which is 2, times 3 raised to the 7 minus 1. Right, again, these are n values. This is an A value. That's the amount at position 1. The 2, I'm sorry. The amount at position 1 should be a 6. Glad I caught that. I put the amount at position 0. We want the amount at position 1. This should be a 6. Times 3 raised to the n, that's our ending position, minus 1. 1 is our starting position. All right, so this is going to be 6 times 3 to the 6th power. So that should be our answer. Now I'm going to come back and multiply by 3 and get to 7 and see if these match.
You done?
Okay, folks, I went ahead and computed the remainder of the sequence, and I found that the amount, if we kept multiplying by 3, the amount at position 7 would be 4374, and I calculated 6 times 3 to the 6th power, and we got 4374. Okay, now, so look at the mistake I almost made. I almost put the amount at position 0 in here. You have to be careful. This value here has to match that value there. Okay, but let's have some fun with this. Let's play around with this formula and recognize that what we're really dealing with is that the amount at your end position equals the amount at your starting position times 3 raised to the ending position minus the starting position. This is the number of steps you're going to take right here. And that's going to be the number of times you're going to multiply by 3. So you're going to take that initial value, you're going to multiply it by 3 this many times. So let's play around with this. Suppose you wanted to find the A value at position 5, and you want to start at position 2. Okay, so this is going to be the position at the amount at position 5 equals the amount at position 2, that's your starting, raised to an end value, that's your ending point, minus the end value, that's your starting point. So let's see if this checks out. Let's see if the amount at position 5 equals the amount at position 2, which is 18, times 3 raised to the 3rd power. A to the 5th equals 18 times 3 to the 3rd power. So 3 to the 3rd power is 27. And let's just see what 27 times 18 is on the calculator and see if it matches what we have on the screen, which is 486. And indeed, this value matches the value at position 5. It's the amount at the end equals the amount in the starting position times common ratio raised to the end minus the start.